So, dear colleagues, we will start today the chain of the meetings with the eminent scholar from India, Dr. Praveen Agarwal, in frames of our scientific seminar, Intellectual Theater. And the first seminar will be devoted to the mathematicians issues. And please, Dr. Praveen, you are welcome with the title of your report. You have 20 minutes.
Yeah, thank you very much, Professor Ruzana, and all my colleagues from the University of RUDN to give me opportunity to share my talk and my research on this platform. So the title of my today's talk is the certain Saigo type fractional integral inequalities and their q-analogues. So I have I belong from the Department of Mathematics at RUDN International College of Engineering, India, as well as I am associated with the People's Federation University of Russia under the project. So this talk is basically connected with our project. So just a moment. Oops. Yep. So the aim of the talk, introduction, certain inequalities involving Saigo type fractional integral operator, Saigo type fractional Q integral inequalities, conclusion, and references. So the aim of the talk, first, from last decades, various types of integral inequalities have attracted the attention of many mathematicians, and also fractional integral inequalities have been found many interesting applications in the field of engineering and physics. Here I mentioned that it is also having the mathematical inequalities are having the well-known connections with the humanities also. So it is a very appropriate to understand the behavior of the inequalities in sense of the mathematics. And after that, we can use this kind of concept in our humanities. So we can use in the English literature, we can use in the some concept in the another kind of the literatures. For example, in the Hindi, in the English, in the Sanskrit, we can use the fundamental concept of the inequalities. But now here I'm talking about the mathematical background of the inequalities. Okay, so here we am to discuss to introduce certain new Saigo fractional integral inequalities and their Q extensions. Then we studied some special cases of these inequalities involving the Riemann-Livoli fractional integral operators, and then study some special cases of these inequalities involving the Adderley-Kober fractional integral operators. So from the last decades, various types of integral inequalities have attracted the attention of many mathematicians, and also fractional integral inequalities have been found many interesting applications in the field of engineering and physics. Very recently, in 2019, Ikni and Ojimer have studied the Hermite type integral inequalities involving the intermediate value of f dash modulus by using the Riemann-Livoli fractional operator, and Butt et al. Established some new integral inequalities involving Caputo fractional derivative for exponential S-convex functions. In this sequence, Kizil and Adik have introduced inequalities for strongly convex function via Atangana-Balano integral operators. Later on in 2022, Kalsums et al. Proposed new integral inequalities of Ostrovsky type by means of newly derived identity and considered some special cases. Our present work is fully motivated by the mentioned works. The Saigo is one of the Japanese professor who is working in the fractional integral operator, is one of the important operators of fractional calculus theory due to the involving of the Gauss hypergeometry function 2f1. 2f1 is a family member of the spatial function. This operator has already found various applications in solving problems in the theory of spatial functions, integral transform, and theory of inequalities. Before the setting out the main finding of our article, it is useful to briefly review the contribution on which it is based. we say that fixed nu belongs to the R, a real valued function, gx defined for x is greater than 0, belong to the function space C nu if there exists a real number q is greater than v such that gx equal to x cube phi of x, where phi of x belongs to the complex 0 to 1. Moreover, for m is belongs to the R, we say that gx belongs to the function space Cm nu if gm belongs to the C nu. The Riemann-Livoli fractional integral operator is defined by the equation number 1. You can see that for a is greater than 0, the Riemann-Livoli fractional integral operator of a function g such that g belongs to the C nu defined by equation 1. So we can easily understand the function is defined by in the form of this formula. So this is the R a0 nu y gy equal to 1 upon gamma a 0 to y minus t raised to power a minus 1 gt dt, where y is greater than 0. On the same line, the Adderley-Kober is defined the new fractional integral operator, which is given by the equation number 2. So you can see that for a is greater than 0, Adderley-Kober fractional integral operator of a function g such that g belongs to the C nu defined by the KAB g of y equal to y raised to power minus a minus b upon gamma a 0 to y t of b y minus t raised to power a minus 1 gt dt. Here b belongs to the R. On the same time, the Saigo fractional integral operator for a is greater than 0 is defined by the equation number 3. You can see that the equation number 3 is defined by the operator I of a dash b 0y gy, and it belongs to the involving the 2f1, where 2f1 is the classical Gauss hypergeometry function, which is defined by the equation number 4. You can easily see that this is the 2f1 is given by the equation number 4, where s of k denotes the Pockenberg symbol. Now, by observing, we know that the Saigo fractional integral operators contain both Riemann-Livoli fractional integral operators as well as Adderley-Kober fractional integral operators. So what do you mean by this comment? The meaning is that if we are giving the specific values of the parameter, for example, if we are taking a dash equal to minus a in the equation 3, then we get the Riemann-Livoli fractional integral operator. On the same time, if in equation 3 we put a dash equal to 0, we get the Adderley-Kober fractional integral operator. So it means that the Saigo fractional integral operator is a more generalized fractional integral operator in comparison to the Riemann-Livoli and Adderley-Kober. Then fractional integral inequalities are an important tool to prove the key result, the uniqueness of the solution of fractional partial differential equation and fractional boundary value problems. Also, they give the information about the boundedness of solution of partial differential equation and fractional boundary value problems. These features have led many researchers in the area of integral inequalities to analyze some more extension and generalization by involving the fractional calculus integral operators. So introduce the following functional. You can see that the equation 7 is represent a functional t k-l-m-n. This is a combination issue that how we can compact to the relationship between the mt, kt, lt, nt, and this combination is defined by the functional t of k-l-m-n. Here KL belongs to the CD closed interval and are two integrable function defined on the interval CD, and MT and NT are positive integral function defined on closed interval CD. So consider two functions phi and psi defined on closed interval CD. Then they are synchronized on CD if they satisfy the following inequalities. This is the beautiful result which is given by the equation number 8. Phi of t minus phi of s is multiplied by the psi of t minus psi of s is greater than equal to 0. For arbitrary t, comma s belongs to the CD, then from 12 and 13, we observe that t of phi psi mn is greater than or equal to 0. You can see that this is a functional t, which we have represented in equation number 7. If the inequalities defined in 8 is reversed, then function phi and psi are called asynchronous on CD and satisfy the following inequality, which is given by the equation number 10. Okay, and for any t, s belongs to the CD. From 14, we have the Chebyshev inequality for the special case when mt equal to psi t, and for any ts belongs to the CD, the functional tklmn defined in 7 has drawn many researchers' attention due to the wide range of application in engineering, mathematics, statistics, probability, transformation theory, probability, and numerical quadrature. From all these applications, the functional tklmn has also been used to produce many integral inequalities. So we can go to the next part. In last few years, many researchers have more attention to the q calculus and fractional q differential equation due to many application of q calculus in physics, statistics, and mathematics. The q calculus are also called the quantum calculus, can be dated back to 1908. Jackson work and fractional q calculus is the q analog of the ordinary fractional calculus. Recently, q calculus operators have been applied in various fields like optimum control problem, ordinary fractional calculus, solution of the q difference, q transform analysis, and q integral equations, and many more such areas. So q-shifted factorial functions, here there are some definitions. You can see that the q-shifted factorial function, which is defined by the equation number 11, and the q-shifted factorial with negative subscript is defined by the equation number 12. Then if from 11 and 12, we conclude the sum of the identities, you can see that the identity number 13, and there is another relation which is given by the equation number 14. Then from the above equation, for any complex number beta, we got the very interesting result, which is given by the equation number 15. Here only the principal value of the q beta is valid for the above equation. From the power function c minus d raised to power minus m, we can define the q analog in the equation number 16. So we are easily compute all the results by using some small computations, and then we can got the result of the equation number 16. Then from the above equation 16, we conclude that the c minus d mq is defined by equation number 17. If m equal to 0, then the value is 1, and when m belongs to the natural number, then it belongs to the c minus dq dot c minus dq raised to power m minus 1. In 1910, Jackson was the first researcher who introduced the q derivative and q integral in systematical way. So the q derivative of the function gx, which is defined by the equation number 18. And from the above, we observe that if limit q tends to the 1, then dq gx becomes the d by dx gx. And given function gx is differentiable. It is easily understand. The equation 19 shows that it is a differentiable function. So the q integral of a function gx, which is defined by the equation number 20, 21, and 22. Then for q is greater than 0 and 1, the q gamma function, it is a very important function, q gamma function, which is defined by the equation number 23. For our results, it is very, very important. And then for b is greater than 0, the q analog of the Riemann-Livoli fractional integral operator is defined by the equation number 24. You can see that in the initial section, we define the Riemann-Livoli fractional integral operator. Here we define the q analog, right? And on the similar way, the q analog of the Adderley-Kober fractional integral operator is defined by the equation number 25. For a is greater than 0, a dash and b belongs to the q analog of the Saigo fractional. So this is the Saigo fractional integral. Its a q analog is defined by the equation number 26. Then this is our first theorem, certain inequalities involving the Saigo type fractional integral operator. Assume U and V are two positive integrable and synchronized mapping on 0 to infinity. Suppose for all positive integrable mapping M1, M2, N1, N2, then such that the relation M1t greater than 0 less than equal to ut less than equal to M2t on the same way N1t is greater than 0 less than equal to Vt is less than equal to N2t, then the following inequality holds true. This result is holds true, and the beautiful result given by the equation 28 holds for the given equations, right? So by using here, I am giving the proof by using the relation that are given in equation number 27, we can easily found the equation number 29 and 30. If we multiply together 29 and 30, then we got the result is given by this term. Then after that, we have after this some computation, the result becomes in result of the equation 31. And considering the following function f of xt defined by this right hand side term is given by this, then multiplying both sides of 31 by f of xt defined by 32 and integrating resulting inequality with respect to t from 0 to x and using the definition 3, we get the interesting result which is given by the 33. Then let us recall the AMGM inequality which is given by the a plus b is greater than equal to 2 under root ab, and by applying the classical inequality to 33 we obtain the result which is given by the equation number 34. By making use of some necessary operations, we deduce that the result comes in the terms of the equation number 35, and this is the proof of the theorem 1. On the same way, if we substituting a dash equal to minus a and a dash equal to 0, then we got the Riemann-Livoli fractional integral operator of the following inequality holds true, which is given by the equation number 36. On the same way, the Adderley-Kober fractional integral operator, the following inequality holds true in given by the equation number 37. Now, the Saigo type fractional q integral inequalities. Here we establish some q integral inequalities involving q Saigo type fractional integral operator, which are the q analog of the theorem proved in the previous section. Now, consider q is greater than 0, less than 1. Let u and v are two positive integrable and synchronized mapping on 0 to infinity. Assume for all positive integrable mapping m1, m2, m1, n2 such that the inequality 38 holds true, and then we got the following interesting q integral inequalities, which is given by this term. On the same way, if we are substituting the a dash equal to minus a and a dash equal to 0, then above result is given to us to the q analog of the Riemann-Livoli fractional integral operator and q analog of the Adderley-Kober fractional integral operator. So we summarize our research work by mentioning that all the results derived in this paper are novel and important. Firstly, we have established certain inequalities involving Saigo type fractional integral operator and derived some special cases of it. Then we have derived q analog of the inequalities involving Saigo type fractional integral operator. That means certain q integral inequalities. Some special cases of q integral inequalities also derived. We also noticed that when q approaches to 1, then the resulting inequalities presented in the section 3 are become those demonstrated in section 2. So I acknowledge this work were prepared within the framework of the agreement between the Ministry of Science and Higher Education of the Russia number 0751520216003 and developed of new methodology and intellectual base for the new generation research of the Indian philosophy in correlation of the main world philosophy traditions. This work has been supported also by the RUDN-University Strategic Academic Leadership Program. And these are my references. You can see that some of my references are, I'm sorry. Yeah. So these are the references which I have used in my work, and this is an interesting work, and we have developed many papers on this direction.
Praveen, we have only 10 minutes till the end.
Yeah, thank you. Thank you very much. Yeah, Rujana, if any question, then please welcome.
No, I think everything is clear. Probably anyone wants to clarify something. I mean, online participants. So there is no question. Thank you very much, dear Professor Praveen, Dr. Praveen. So I think today we will finish and we will continue our meeting in several days. Okay?
Yeah.
So
Thank you very much for giving me opportunity.
This recording will be posted on YouTube channel of our center. So we will send you link as soon as we post it.
Yes, okay? Yes. I request to the Lilia, please share me the link. Okay.
Yes. Okay. Thank you very much. Bye. See you later.
Bye-bye.
So I'm waiting for information. Okay. And we will send also our information you.
Okay. Thank you. Thank you, Lilia.
Okay.
Thank you, Ruzana.
Bye.
Bye-bye.
Send my greetings to your son and your wife, your family.
Yeah, thank you very much. And give my greetings to all the friends of the Russian.
Okay. Thank you.
Thank you.